The video today is on the equations for gas laws. So there's four of them that we're going to learn: Boyle's, Charles, Amontons, and the combined gas laws. We're going to start with Boyle's Law. It comes from an Irish scientist, Robert Boyle, who lived in the 1600s. And he discovers a relationship between the pressure of a gas and the volume of a gas. So we're going to see these abbreviated with the initials P and V. And he sees that the relationship is inversely proportional. That is, if pressure is going up, then volume would have to be going down. And if pressure were going down, then volume would have to go up, assuming a lot of other things stay constant, assuming the amount of gas stays the same, so you're not changing the moles, and assuming the temperature stays the same, so you're not moving it up or down. So this is a relationship in which one variable increases proportionally as the other variable decreases. The way that this law is actually written is the volume of a fixed amount of gas held at a constant temperature varies inversely with the pressure. So things that are held constant here, things that don't change. Okay, we should make a note of that. A fixed amount of gas, so that means the moles are constant, held at a constant temperature. Okay, so moles and temperature are staying the same. Pressure and volume are going to change. Okay, our variables are P and V. It does not require any specific units, but you have to be consistent with whatever units you choose. So if one of the parts of the problem says atmospheres for pressure and the other part says torr, well, you're going to have to be consistent. One of those is going to have to get converted. Okay, so here's just a way of describing this law. Okay, so Boyle's law looks like what you see right here. P1V1 equals P2V2. That is the pressure times the initial volume, initial pressure times initial volume equals final pressure times final volume. If you were to graph this, you get kind of a descending curve. Okay, so notice we have sort of an asymptote here on the y-axis and on the x-axis. And over here you can kind of see with this picture what's going on. This is the initial set of conditions here. 1 atmosphere of pressure and 10 liters according to our diagram. Okay, and here if we cut that volume in half, so V went from 10 to 5, the pressure has doubled. Okay, and I get a constant here, so 10 atmosphere to liters is what that unit looks like, 2 times 5. So if I cut the volume in half, the pressure went up twice the amount, so from 1 to 2 for the atmospheres and down from 10 to 5. So that's the relationship there. If you were to cut it in half again, your pressure doubles another time up to 4 atmospheres, and your volume would get cut in half down to 2.5. So there's our relationship, and that's what you can see what's going on over here. So let's try a problem for this. We know it's a Boyle's Law problem, so let's just go ahead and write our equation. P1V1 equals P2V2. It says a diver blows a 0.75 liter air bubble 10 meters underwater. As it rises to the surface, the pressure goes from 2.25 atmospheres to 1.03 atmospheres. What will be the volume of the air bubble at the surface? Okay, so my initial pressure, my P1 here, is 2.25 atmospheres. And it looks like my initial volume was 0.75 liters. My final pressure is 1.03 atmospheres, so we're saying that's what's at the surface of the water. And what I want to know is how big is that bubble? What happened to it? Well, we can kind of make some assumptions here. The pressure went down, which means my volume is going to have to go up. And I'm solving for V2. So if I rearrange this for V2, this is V2 is equal to P1 times V1 divided by P2. And if we set that up, initial pressure is 2.25 atmospheres. Initial volume is 0.75 liters. Okay, all divided by P2, which is 1.03 atmospheres. All right, and if we plug that into a calculator, we are going to get, with two significant figures because of 0.75, we are going to get 1.6, and notice what happens to my units here. atmospheres have canceled, and the only thing I'm left with is liters, so 1.6 liters. So that air bubble has more than doubled in size. It went from 0.75 liters to 1.6 liters. And that would be your final answer there. So pretty easy. Okay, so we're going to look at the next law called Charles' Law. This is a French guy. He observed that as the temperature increases, the volume of a gas also increases when the amount of gas and the pressure remain constant. Okay, so let's look at, according to this definition here, things that are constant, the amount of gas, so the moles, and the pressure, right, P. The things that are changing this time are temperature and volume. So if we're labeling our variables, right, temperature and volume are going to change. And he says that as one goes up, the other one goes up. As T would increase, he would notice that the volume would increase. So this is a flexible container, like a balloon or something like that. Or if T went down, if we lowered the temperature, then the volume also would go down. So here's his equation. V1 over T1 equals V2 over T2. Initial volume divided by initial temperature is equal to final volume divided by final temperature. The volume of a given amount of gas is directly proportional to its temperature in Kelvin at constant pressure. Okay, so this time around, instead of being inversely proportional, it is directly proportional. What happens to one variable is the same thing that happens to the other variable. Notice my temperature must be in Kelvin. If you don't do that, you're going to get a wrong answer. If you try plugging in Celsius here and you have negative temperatures in Celsius, it's not going to work because you would end up with negative volumes as an answer. So we have to be in Kelvin. The unit for volume, once again, doesn't matter too much, but you have to be consistent. Right? You have to keep it in probably liters. So it says just a moment ago that Charles' law is directly proportional. As one variable goes up, the other variable increases proportionally. The graph here results in a straight line. So as before, where you kind of had that downward sloping curve, what we are going to have here is a straight line. The graph, if you notice, okay, starts at 150 Kelvin and goes upward, saying that it would take up 300 milliliters, and at 300 Kelvin it would take up 600 milliliters. Okay, if you went up to 450, it'd be 900 milliliters. Well, what's going on with this part of the graph, where we have this dashed line down to 0? Because if V is 0, then T must be pretty close to 0 as well, right? So what's going on with our dashed line here? Well, that is an assumed calculation. We are assuming that those are to be true. That's saying that at less than 150 Kelvin, whatever gas this is not a gas. Right? We're saying that that is actually a liquid. Okay, and they're working backwards to find the 0, 0 point, because it's got to go through that point as well. So this is theoretical here, from 0 to 150. Okay, we don't know that for sure, but that's because it's not a gas, it's a liquid, and we can't apply a gas law to a liquid. So this is just kind of a diagram over here to the side where you can actually see these sort of things going on. So here's my flexible container. This time we have a piston set up, okay, a plunger. My container is 300 milliliters, and it's got 1 atmosphere of pressure. Okay, so normal sea level pressure. If we were to heat it up, though, okay, to say 300 Kelvin, so it's normally at 150 here, so that's pretty cold. 300 Kelvin, that is slightly more than room temperature, just to give you an idea. But notice the pressure stayed the same. The pressure was 1 atmosphere in both cases. And in order for that to happen, the volume had to double. Otherwise, the pressure would have doubled here. So the pressure stays the same, but my volume doubled to make that happen. So that's how we get this point here at 150 Kelvin at 300 milliliters. And if we heat it up, double the temperature, then we've doubled the volume. That's what this graph is doing. Okay, so let's try this one. A helium balloon in a closed car occupies a volume of 2.32 liters at 40 degrees Celsius. This is a hot car here. 40 degrees Celsius, we're talking about like, 110, 115 degrees Fahrenheit in there. If the car is parked on a hot day and the temperature rises to 75 degrees Celsius, so once again, leaving it out with the windows up, it gets real, real hot in there. What is the new volume of the balloon, assuming the pressure remains constant? Okay, so the balloon's allowed to get bigger. Well, my initial temperature here, T1, we're saying is 40 degrees Celsius, but the problem with that is it must be in Kelvin. So we're going to take 40, and we're going to add to that 273, and that should give us 313 Kelvin. You have to do that, or this problem is not going to work. My initial volume was 2.32 liters. T2, so 75 degrees Celsius. And we got to convert that over to Kelvin, so plus 273. And that is 348 Kelvin. V2 is what we are solving for. So back to my equation. V1 over T1 is equal to V2 over T2. The variable we are solving for here is V2. We have to be careful, right? Using algebra, sometimes this one gets messed up. It actually gets messed up quite a bit. If I bring T2 up to the top side on the left, I end up with the equation V2 is equal to, and I have V1 times T2 divided by T1. And I can't tell you how many times, guys, I put V1 times T1 divided by T2. If you do that, you're going to get the wrong answer. Keep in mind that we know that since it's Charles' law, that if the volume goes up, the temperature also has to go up. They are directly proportional. So my temperature went up here, went from 40 to 75 in Celsius, which means my volume must go up. So if I get a volume smaller than what I started with, that means I flipped T2 and T1 when I tried to solve for this, and you should know your answer is wrong. Okay, so for V2 then, if I take V1, 2.32, multiply times T2, which is 348, and divide by T1, 313, I end up with, and we are going to treat it as three significant figures for the temperature. This is going to be 2.58 liters. Okay, that would be our answer here. So it only went up a slight amount. It's something close to like 10% or so of what it was initially. So not a whole lot, even though it went up 35 degrees Celsius. Okay, and on to Boyles Law, which is sometimes called Gay-Lussac's law as well. The pressure of a fixed amount of gas varies directly. Okay, so we have inverse and directly with the temperature in Kelvin when the volume remains constant. Okay, so once again, what things are constant here and what things are changing? Our constants, once again, a fixed amount of gas. That means the moles don't change. My physical amount does not change. With the temperature in Kelvin when the volume remains constant. So V is constant here. I have a rigid container. It's not allowed to expand like a balloon or a plunger or a piston or something. And the variables, things that are changing, pressure and temperature. And it says it's directly proportional, meaning that if the pressure goes up, then so must the temperature. Or if the pressure is going down, then the temperature must be going down. Whatever one does, the other one does. The equation we get for Boyles' law then, all right, writing it with the correct subscripts here, P1 over T1 is equal to P2 over T2. That's what it should look like. And it's directly proportional, so we get the same kind of line as Charles' law, where we get this straight line. Boyle's is inversely proportional. You get that downward sloping curve. The other two are straight lines. So here's kind of what's going on in this picture. I have a rigid container. It can't change volume, so it's 1 liter. And here it's 1.5 atmospheres worth of pressure at 150 Kelvin. And over here we've doubled the temperature to 300 Kelvin. And look what happened to the pressure. It doubled. So here we're marking our points there. And once again, this really probably at this point, temperature in Kelvin, once you get below a certain point here, you're actually not going to be a gas, so this would be more of the theoretical range, but it should run through 0, 0. If I don't have any temperature, that means I don't have anything moving around, and if I don't have anything moving around, I can't have anything applying pressure to the walls of the container, so it should run through 0, 0. Okay, the problem here, the pressure of the oxygen gas inside a canister is 5 atmospheres at 25 degrees Celsius. The canister is located at a camp high on Mount Everest. If the temperature there falls to negative 10 degrees Celsius, what is the new pressure inside the canister? Okay, so we know this is an Boyles Law problem. P1 over T1 is equal to P2 over T2. Let's go ahead and label some stuff here. My initial set of conditions. My P1 is going to be 5.00 atmospheres. Okay. My initial temperature, T1, can't be in Celsius. I got to convert that over to Kelvin. That is 298 Kelvin. So that's basically room temperature. P2, all right, well, that's what it wants to know. Like, how much pressure does this thing actually have if I've dropped that amount degrees in Celsius? And T2 can't be negative. This is where if you tried to plug this in, you'd end up with a negative pressure, which doesn't make sense. Negative 10 plus 273 is 263 Kelvin. So I'm solving for P2 here, which means, once again, I got to take T2 and bring it up to the top. So that's a classic mistake when you were trying to do this. In solving for P2, we get P1 times T2 over T1. Make sure you put the things in the right spot. Okay, make sure you do that. And since we know it is directly proportional, if the pressure is rising, the temperature must all be rising. And if the pressure is going down, then the temperature also must be going down. So if you didn't do this rearranging correct, you should actually get the wrong sort of relationship here. So let's go ahead and plug stuff in. P2 is equal to, well, P1 is 5 atmospheres. T2 is 263 Kelvin. Divided by, okay, T1 is 298 Kelvin. All right. And my answer here to 3 significant figures, run this on the calculator, is 4.41 atmospheres. So it's actually lost about a little more than 10% or so of its pressure just by the temperature drop there. 4.41 atmospheres. Not as much pressure with the cold temperature. What if multiple variables change? The combined gas law, so this is the last one listed here, states the relationships between pressure, temperature, and volume of a fixed amount of gas. So things that are constant in a combined gas law problem, there's only one thing, moles. The variables are 3 things here. Pressure, temperature, and volume can all be changing. So what happens if you're changing multiple things at once? That's what the combined gas law is for. Well, it's actually not too hard to remember, because if you can remember the combined gas law, you know all the relationships. The relationships are the same as the previous laws, just combined. Okay, so Boyle's was pressure times volume, Charles was volume over temperature, Amonton's was pressure over temperature. Well, if I keep those 3 and I combine them all, I end up with PV over T, and that's consistent across these 3 here. So if I have P1 V1 T1 over T1, I should have that equal to P2 V2 over T2, and that's what we get with the combined gas law. So I can actually change 5 things at once and still get the right answer. It allows you to solve problems with changes in more than one variable. Okay, so let's go ahead and try this problem. A gas at 110 kilopascals and 30.0 degrees Celsius fills a flexible container with an initial volume of 2 liters. If the temperature is raised to 80 degrees Celsius and the pressure increases to 440 kilopascals, what is the new volume? So let's just go ahead and take stock of what we got. My initial pressure is 110 kilopascals. My initial volume, we said, is 2.00 liters. And my T1 cannot be in degrees Celsius. It's got to be in Kelvin, so 30 degrees Celsius has become 303 Kelvin. My P2 is 440 kilopascals. My V2, well, that's what I'm solving for. And T2 is 80 degrees Celsius, but that's got to be in Kelvin, so 353 Kelvin. I'm solving for V2, which means T2 is going to come up to the top, and P2 is going to come down to the bottom, right? Just rearranging using algebra. I get V2 is equal to P1 V1 times T2, all divided by T1 times P2. So let's go ahead and plug those values in. P1 is 110 kilopascals. V1 is 2.00 liters. T2, so make sure we put the right one there, 353 Kelvin, divided by, T1, 303 Kelvin, times P2, which is 440 kilopascals. And if you're curious, just watch what happens to the units. Kilopascals cancel, Kelvin cancels. All we're left with is liters, which is good because we want a unit of volume. And that whole thing plugged into a calculator. Let's see here. And we get, and we're going to go with three significant figures, 0.583, and my unit is liters. So the volume almost got cut down by about 70% or so, down to 0.583 liters. So here is a nice summary of all the gas laws. So if you are trying to figure out what you're supposed to use, take a look at that. And the problems that you've got for homework, look at what's changing and what's constant. Okay, if something's not changing, then it's not a part of the equation. You only have to use what's changing to solve. Okay, so this would be a nice, helpful summary for that.